the concentrations of microplastics in the organisms, we saw that for Hylolantheca, the other shrimp, the one that was not affected, we didn't find any particles on the feces or in the body of these organisms. However, when we looked at the microplastics inside Gammarus pulex, we saw that there was a positive relationship between the number of microplastics inside the body of Gammarus pulex and the number of microplastics in the sediment. So the more plastics in the sediment, the more plastics were found in Gammarus pulex. That was in number of particles, but if we transform this in weight, we also saw the same linear relationship. So the weight of the particles in the organism by the weight of the particles in the sediment. This is only in the organism, so after the desiccation, there were still particles inside these organisms. And for the feces, we saw the same relationship. So this means that over time, they were not able to excrete all the particles, and that's why we found particles in the feces and in the body. Also, when we looked at the particle size distribution of the microplastics in the total microplastics that they ingested, we saw that there was an upper limit and a lower limit. So these organisms ingested particles with sizes between 30 and 165 micrometers. So not all the range that we added. So only part of the plastics that were bioavailable for these organisms. So in the end, actually, the concentration would be lower. So our conclusions are that the exposure to polystyrene microplastics caused no effects on any of the species tested, except for Gammarus pulex, for which a significant reduction in growth was found. Particle ingestion significantly increased with the concentration in the sediment, and here again size matters because microplastics were ingested from a specific size range. If you remember, I showed you that for Hylolantheca, the shrimp that was not affected in the study was affected in another study. And in that study, they used polyethylene microplastics, and they didn't use sediments, so these particles were more in the water column. And they were also smaller, so they had a size between 10 and 27 micrometers, so maybe this species affected by smaller microplastics, but also, as I said, the bioavailability, because polyethylene has a lower density than polystyrene, so it can longer remain in the water column, while polystyrene has a higher density than fresh water and will more easily stay in the sediment and be less in the water. However, Gammarus pulex has a characteristic that is creating a lot of bioturbation in this system, so they respend these polystyrene microplastics very easily, so they are more easily exposed to them. And I will conclude talking a little bit about the implications in risk assessment. This is a way to do a risk assessment, and it's called the tier approach, which consists of different tiers. And the first one, which is the number 0, is based on theoretical models, so it's not based on experimental data. But tier 1 is what we just did. So it's doing standard single species test battery, and with this tier you can already know how it would, what the risk would be. And then there are higher tiers, and like the core and additional sediment toxicity data that I will explain also a little bit later. So we have the data from the study that we did, in which we found this 3.77% of plastic in the sediment that affected the organism, and with that value we can calculate a predicted no effect concentration of 0.189. This conversion is based on assessment factors, which is quite complex to explain, but there is a list, and depending on how many species you tested and which species you use, they give you a value to divide your value by this one. And then we got this percentage, and then we have a predicted environmental concentration, which can be realistic. This means that this is what could be found in a freshwater sediment. And also a worst case scenario, which is the highest concentration ever found in a freshwater environment, which is not what a normal species would find, but which in several occasions could occur. So I compared this value, the predicted no effect concentration, And I compared it with the predicted environmental concentration, and I calculated the risk quotient, and as it was below 1, we can conclude that there is no risk for these organisms. Not in a realistic scenario, but also not in a worst case scenario. But if we would go to the next year, which is for an additional sediment toxicity data, which means that you have your data, but you also look for all the data in the literature of studies that could be comparable with yours, and you make an SSD, which is a species sensitivity distribution. And this is what I did here. I will explain how I did it, because this is a little bit related with the exercise that you will do, so it's good that you try to understand how it works. It's again not an ideal SSD, because with microplastics it's very difficult to have ideal situations. There is almost no data, so okay, what can I do? What I did was to calculate the lowest observed effect concentration. If you remember, is the lowest concentration at which an effect was found. So in my case, I have my dose response curve, and I can calculate which concentration this was. And I look for that also for other species, for other invasive invertebrates, and as for freshwater organisms, I only found one other data, which is this Diptera. The rest I took from marine organisms, so which were exposed via the sediment. So, there were different polymer types, which I distinguish here: polyethylene and polystyrene. And it also included different endpoints. So this was affected, this is a clam, and it was affected by chlorophane content decrease exposed to polyethylene. Here, this Diptera was affected under survival, growth, and emergence, and these are the concentrations at which they were affected. In this case, it's the number of microplastics per kilogram of sediment dry weight. So with this type of graph, you can look at which species are more sensitive. So you have all the data, you have all the lowest observed effect concentrations, and you can plot it in this FSD. And with this, you can also calculate the risk, which in this case is quite interesting, because of course I don't have much data, and if you really want to make a good SSD, you need to have a wide range of organisms, and for the same endpoint and for the same particle type, but this is the best I could do. And based on this, there would be a risk, because based on this, 21% of the species would be affected because they would be affected by concentrations that are higher than the predicted environmental concentration, which is here in particles per kilogram. So what this shows is, for instance, if we have the concentration, the environmentally realistic concentration, we would see that it's here, so that this species would be affected in the environment. And this is just in the realistic scenario, so in the worst case scenario it would be worse. So, in my opinion, there is not sufficient data yet to conclude, oh yeah, there is risk, because it's two studies where they found effect on two species. And what I also find interesting is that polyethylene seems to be affecting more the species than polystyrene. And yeah, of course, hopefully over a few months or years I will be able to really make a proper SSD, which was my aim, but of course I didn't find effects on 5 out of 6 species, and I actually tested more than the ones that I showed you here, and I didn't find any effects, so only in one species. So I cannot do an SSD with my own data, which was what I wanted, but I have to compare it with other studies, and that makes it complicated. So this still has to be done in more detail. And just to conclude, the next step would be to do field studies, which I also did during my PhD, in which I exposed a community in an outdoor system to nano and microplastics via trace. And I will go very quick on this. So we tested the effects of the same microplastics that we used in the single species study, and also nanoplastics that we created here at the university on a benthic community, which was composed by very different benthic invertebrates, and we exposed them for 3 months and also for 15 months. And for this, we mixed these plastic particles with the sediment, and we added them in trays, separately the microplastic from the nanoplastics, at 5 concentrations, from which 2 were environmentally realistic. The green ones are below the highest concentration ever found. The yellow one is 5 times higher than the highest concentration found, and the red one is very high, unrealistic, but also interesting for us to try to measure these effect thresholds for a community. We again have 4 replicas, and we had trays made that were going to be retrieved after 3 months and after 50 months. So in total we had 80 trays that we spread over the ditch. For this we used the block design, so we divided the system in 4, and we mixed the replicas, each of the 4 replicas in one of these blocks. We also took transects to know how the donor community was composed. And this is how it looked like. And you will ask, oh, is it a plastic tray what you're using? Yes, because it was not ideal. It's a different polymer type than what we use, but when you work with this, it's very difficult to avoid plastic, which is always very difficult in all studies, because if you use glass, someone can fall and break a leg or whatever. So, or they can just go very deep in the sediment, and then you cannot retrieve them. So that makes it difficult. Yeah, we quantified the amount of plastics in the trays, and we saw that they were linearly increasing the nominal with the actual plastic concentrations that we measured and found. So the result that we found was that there was an effect in the number of individuals. So we retrieved the trays and we counted the number of individuals, and also we defined which taxa they were. And we saw that at the highest concentration for both nano and microplastics, there was a clear decrease in the total number of individuals found in the trays. And when we looked at the individuals per class, so there were different classes of individuals, we saw that actually this reduction was mostly caused by the class clitellata. So for the rest, especially after 15 months, they were quite similar. They had a similar proportion, but when it came to this orange bar, which is the class clitellata, this reduction was also found. So we looked at the effects of these microplastics on the number of Landidae worms, which are small worms, like the ones that you can see in the picture here, which were actually also tested in the single species toxicity test, and there we didn't see any effect. But it seems that over time, after 15 months, this reduction in the worms was appearing. Also, we looked at the number of taxa, and there were no differences among treatments, although there was a difference over time. So there were a higher number of taxa after 15 months than after 3 months. And we also looked at the diversity. So Shan diversity index is a way of measuring the biodiversity, and we also didn't see a difference between treatments, but we saw that in general it decreased over time, except for the highest concentration, which could be caused by this reduction in the number of worms, because this biodiversity index takes into account the number of taxa and how many organisms are from this taxa. So if you have a very abundant species, like a worm, this amount decreases, this value decreases. So we concluded that there was an effect of time, spatial distribution, which was the block, and the concentration in the number of individuals found in trays, and that this was caused by a reduction in the abundance of Landidae worms. However, no ecological risks were found at the current environmental plastic concentration. So as I said, this happened for the highest concentration, which was 50 times higher than the worst case scenario. So in reality, worms would not be affected with the concentrations that are out there. And to conclude, this is how it can be calculated with this value. So the predicted effect concentration would be here the no effect concentration, and based on this we would conclude that there is no risk. So thank you very much for your attention. You've been very quiet, but it was really nice. Thank you. Are there questions?
Have you completed this research?
Sorry?
I mean, you completed your research, I'm still working on it.
I'm still working on it, so this last data that I showed you is not published yet. Hopefully it will be published in a few months. The single species toxicity test has been
Do you have some outcomes of your research in terms of finance?
finance. If we have
I
progress.
mean, we do research for solving the problems, exploring ideas to get a degree. To say that is this lucrative research?
Literature.
Lucrative.
I cannot hear you, sorry.
Is this a lucrative research?
It's a TCW project in which we are working. So it's a project, it's a national project, it's a national funding, where also water boards are participating. So it's not paid by the industry, if that's your question. Lucrative means like if a plastic company wants to. What's that? Or
How do you get some benefits in terms of finance?
how you get finance for this? Well,
You're doing good research and benefits.
I think we might better discuss it with the copy because it seems like complicated. We're talking about finance because for me it was a job opportunity, so I don't know so much about how to find